In this video, we demonstrate an example of an application of the method of cylindrical shells in finding the volume of a solid of revolution generated by rotating around the y-axis, the region whose boundary is made up of portions of the graphs of f of x equals the square root of x, g of x equals 2 minus x, and the x-axis. Let us call this region region R. As we speak, the solid of revolution is being generated on the right panel as region R rotates around the y-axis. Before we set up the volume integral or integrals for the solid of revolution, let us review the cylindrical shell's integral formula for a basic solid of revolution. If the region generating the solid of revolution is bounded above by the graph of h of x equals y, and below by the interval from x equals a to x equals b on the x-axis, then the volume of the solid of revolution is 2 pi times the integral from a to b of x times h of x. We are going to adapt this formula to the solid of revolution in our exercise. Going back to region R in the exercise, while the lower boundary is a single interval on the x-axis, its upper boundary is made up of 2 pieces. A vertical line through the point where the graphs of f and g intersect forms the boundary between the 2 pieces of region R, and so one portion is bounded above by part of the graph of f, and the second portion is bounded above by part of the graph of g. And so the solid of revolution is made up of 2 solids of revolution. One solid, which is the inner part, is generated by the region bounded above by f of x equals the square root of x. The second portion, which is the outer part of the entire solid of revolution, is generated by the region bounded above by g of x equals 2 minus x. This part of the solid of revolution looks like the lower portion of a cone, or what is called a frustrum of a cone, with the central core taken out. So we will need 2 integrals, one for each portion of the entire solid of revolution described in the exercise. We call the volume generated by the region bounded above by f of x equals the square root of x, volume sub f. When we insert an approximating rectangle for the region used for generating a solid of revolution, the factor x in the basic volume integral represents a distance of the rectangle to the axis of rotation, which is the y-axis. And so we can take this distance to be any x-coordinate within the rectangle. The factor h of x in the basic volume integral stands for the height of the approximating rectangle. For volume sub f, we take this height to be f of x. The leftmost point of region R is at the origin where x equals 0, and so the lower limit of integration for volume sub f is 0. The upper limit is the x-coordinate at the intersection between f and g. To find this, we set the square root of x equal to 2 minus x. We square both sides and put all the quantities on the right side. So we have 0 equals 4 minus 5x plus x squared, which factors out into the quantity 1 minus x times the quantity 4 minus x, so that x is either 1 or 4. F of 4 equals the square root of 4, which is 2, And this isn't equal to g of 4, which is 2 minus 4, which is equal to minus 2. So the intersection cannot be at x equals 4. And so the upper limit of integration for volume sub f is 1. Therefore, volume sub f equals 2 pi times the integral from 0 to 1 of x times f of x, which is the square root of x, dx. We leave it as an exercise for the viewer to carry out the integration and check that volume sub f is 4 pi over 5. We now turn our attention to the portion of the solid generated by the part of region R bounded above by g of x equals 2 minus x. We call this portion volume sub g. The lower limit of integration for volume sub g is at x equals 1, which is the upper limit of integration for volume sub f. The upper limit of integration for volume sub g is at the x-intercept of g. We set 2 minus x equal to 0. And x equals 2 at the x-intercept of g. The factor x for volume sub g is still x, since the axis of rotation is still the y-axis. The factor h of x in the basic volume integral this time is g of x, or 2 minus x. And so volume sub g is 2 pi times the integral from 1 to 2 of x times the quantity 2 minus x. The viewer can carry out the integration as an exercise and check that volume sub g is 4 pi over 3. Therefore, the total volume of the solid of revolution is 4 pi over 5 plus 4 pi over 3, and this is equal to 32 pi over 15.